Good afternoon, everyone. I'm Rakhi Yadav, your PMRF teaching assistant for pericyclic reactions and organic photochemistry course, which is conducted by NPTEL, and whose course instructor is Professor S. Sankararaman from IIT Madras. So, students, in this last week, I'm going to recap all all the things which you have studied in this course, starting from electrocyclic to your photochemistry of singlet oxygen. So we will start from zero, and on behalf of that we will solve some problems. Let's wait for 1 to 2 minutes for students to join. Aarti, am I audible?
Yes, ma'am.
Hello. You can write in chat if you are not able to unmute yourself. Are my screen are hello?
Hello. Yes, ma'am.
Okay, okay, Aarti.
Okay.
So if any one of you have any doubt at any place, just stop me and ask. Okay. So let's start revising from zero. So students, in this course, we have covered pericyclic reactions and organic photochemistry. As I have told you earlier also, pericyclic reactions are nothing but in these reactions, bonds are made or broken in concerted way. There are no positive charges involved, positive or negative charges involved. Okay. And moreover, they are characterized by cyclic transition state. So, at first, we have studied electrocyclic reactions. These are single component reactions, right? Then we have studied cycloaddition reaction. After that, we have studied sigmatropic, followed by cheletropic reactions and group transfer reactions. So, in pericyclic reactions, mainly we have covered these five reactions. First, I will give you brief recap, then we will solve questions. So, at first, I have taught you how to draw molecular orbitals, right? Since 4 pi electrons are there in this butadiene system, so we have drawn 4 molecular orbitals, right? One, 2, 3, 4. Four molecular orbitals, and number of wave function is equals to number of molecular orbitals. Let me write this thing. Number of wave function is equals to number of molecular orbitals. Since there are four molecular orbitals involved, there are four wave function. They are nothing but your psi 1, psi 2, psi 3, psi 4. Then I have told you, let's say this system is given to you. This system may be subjected to your heating condition or your H mu condition. So, how to see HOMO-LUMO? For that, first you should know what is HOMO. HOMO is your highest occupied molecular orbital. So among the, since you know there are 4 pi electrons, right? So you have to put them 1, 2, 3, 4. Now they are asking HOMO. Among these four wave function, which is your HOMO? So highest occupied molecular orbital is your psi 2. Okay, and lowest unoccupied molecular orbital is your psi 3. But this is the case when condition is your thermal. But when condition will be H mu or photochemical, one of the electron will excite from psi 2 to psi 3. Let me redraw. This is in case of heat, this is case in H mu. When you shine light on this compound, one of the electron will excite. Now, this is HOMO and this is LUMO. Understood, Aarti? Okay. So, in electrocyclic reaction, your first task should be you should know whether it is 4 pi system or 4n plus 2 system. Okay. Butadiene is your 4 pi system. Now, now you know that this is 4 pi system, and you also know that in heating condition this is homo, and in HMU condition this is homo. Now, since only last orbitals are going to meet, right, on electrocyclic they will form this ring. So you should know that only last orbit, if only last carbon molecular terminal carbon molecular orbitals are involved. So let's say this butadiene is left in heating condition. In heating condition, psi 2 is homo, and orbital sign is different, means plus minus minus plus. So if you want to meet these orbitals in a constructive way, right? So you will rotate this first molecular orbital in right side, or I can say that clockwise direction, and this in left side. After that, they will be like this. Yes or no? And this type of rotation is your, sorry, this bond will also move in this side also. Okay, then only negative charge will come here and positive charge will constructively overlap with this. So this is your cone rotation. Cone. So from here we can
So
derive
from
one
here we
thing,
can derive.
that when your system is 4 pi, condition is your heating, then it will undergo cone rotation. Now let's say in HMU condition homo is this, means end orbital sign is same. For that, they will undergo disrotation to have constructive overlap. So, 4 pi in HMU condition will go disrotation. So, from here you can derive your Woodward-Hoffman rule. Let me repeat. First, identify which type of system is this, either 4 pi or 4 pi or 4n plus 2. Okay. Then you should know in heating condition which type of rotation it will go, and in HMU which condition. 4n plus 2 will be just opposite to that. In heating it will go dis, and in HMU it will go cone. I hope you all are clear till this point. This is all about your electrocyclic reaction. In this way, by FMO approach, you are going to derive your Woodward-Hoffman rule, and you just have to rotate these uh, bonds in order to form this cyclobutene. Understood? Okay. After that, they have covered cycloaddition reaction. In cycloaddition reaction, there are two components, unlike in your electrocyclic reaction. In electrocyclic reaction, only one component is there. Cycloaddition reaction can be broadly divided into two parts. So 2 plus 2, 4 plus 2. These are your simple 2 plus 2. These are, and this is your Paterno-Bucci reaction, which you will study in photochemistry. Okay. In this case, we will study more. We will have more focus on 4 plus 2 reaction. This is your Diels-Alder reaction, 1,3 dipolar and pleiotropic reaction. So this is the brief summary which I have kept here. So if you remember how to see regio selectivity in the Diels-Alder reaction, I have told you that just for understanding purpose, you can see that this oxygen lone pair will come here and net negative charge will come here. Yes or no? And in this case, where will be the positive and where will be negative? Arti, in this dienophile. Obviously, positive charge will be here, right? Alpha beta unsaturated system. positive, negative, that will form your enolate type. So obviously this carbon is going to connect to this carbon, right? This terminal carbon of diene will be attached to your alpha carbon of dienophile. Moreover, you should remember that diene should be electron rich and dienophile should be electron deficient. Okay, so this is your 1,2 product that is major. So whenever you are having this type of system, you have to take 1,2. If two options are given to you, your major product will be this. Understood? Okay. In case 2, when two substituted diene will be there, how are you going to solve this question? So obviously when you will draw its resonating structure, right? This negative charge will come here. It can't come here. Yes or no? And this is going to meet at this point. When you will draw, you will find that 1,4 product will be major. Understood? They have just inverted this, okay, and joined this carbon and this carbon, and you will get 1,4 product. I hope I am clear. So this is how you have to see regioselectivity in Diels-Alder reaction. So if any options are provided to you, you have to see either 1,2 product will be major or your 1,4. When the substituents are attached at terminal position, 1,2 product will be major, and when the substituents are at internal carbon, 1,4 will be major. In this way, you can memorize it. Okay. Next comes stereoselectivity of Diels-Alder reaction. All these things will help you in solving assignment and moreover exams which you have to give for this course. Okay, so listen carefully. I will ask in the end of the class. So, how to see stereoselectivity? See, as we have studied, pericyclic reactions are concerted reaction. So, they will be stereospecific. Okay. Since this this olefin is your cis, so in product also this hydrogen will be cis, not trans. So, this is correct, this is incorrect. This is the case when you have to see stereo of your ene, dinophile. And if you see here, they are trans. So yeah, in product also they are trans, not cis. Now, what happen if you are having this? For this, I've told you previously that how to draw. Let me take pen. You just have to draw line, a straight line, and you have to put your dye in. Whatever way in substituents are given to you. B, A, B. And you have to put your olefin in endo way. Endo way means let's say here substituent is B. And this B should be electron withdrawing. Remember this thing. This B should be electron withdrawing. Just keep in mind that B should be pointing towards your dye. This should be your approach. Your dinophile should approach in endo way. Okay. Now whatever substituents are coming on line and left to line, on line and left, give same stereo. And whatever substituents are right to this line, give different stereo. If there is any doubt, ask me now only. Now let's say in this case A and A will be on line, so they are cis. Let's say B is also there, then that B should be that B should be relatively cis to your A. Okay. Here confusion comes because I have taken same. You can assume it as another group G. And see, these groups are at right side of line, this B. Therefore, they are at different stereo. But they will be same. Different stereo with respect to A. Okay. Understood, Aarti? Okay. So, first question is this: major product formed in the given reaction sequence is. You first try, Aarti, and tell me which type of reaction is possible here among electrocyclic and cycloaddition. Please try to unmute yourself
Diel-Saldar reaction, cycloaddition.
and tell me which option is
And tell
most
me which
appropriate.
option is most appropriate.
Your voice is not coming. Okay, write in chat which reaction is possible there. Yes, very good. So there, cycloaddition reaction is possible. Why? One thing is there are two components. So obviously cycloaddition reaction will take place. Now Aarti, tell me if you are thinking that it will be Diels-Alder, which option will be most appropriate? Actually, Aarti, it will be difficult for me to go back to that screen. If possible, try to unmute yourself. Okay.
Okay.
So
So
let's say a simple
let's
question
say
is
a
given
simple
to you.
question is given to you.
Your
Your
cyclopentadiene, and
cyclopentadiene,
let's say here
and let's
CHO
say here
group is there.
CH2
Okay.
group is there.
So
Okay.
in this case,
So in
students,
this case, students,
you just have to draw
you
this
just have to
bridge
draw this
bicycle
bridge
system.
bicycle system.
Okay.
Okay.
This is your five membered
This is
ring.
a five member.
And this bridge I have drawn like this. Okay. So obviously double bond will come here. And these two carbons are going to connect to your diene. Now there are two phases possible for CHO. This is your exophase, exo, and these are your endophase. But due to secondary orbital interaction, in principle, endo product is favored. Okay, so obviously CHO will come down. Now taking help of this example, Aarti, tell me which option is correct. Okay, okay. So option number C you are saying. See, Aarti, if you go back to your regioselectivity, right? And let see here, forget about this part. Forget about this part. Just you remember that this is your diene. So if you see your OMe is at internal carbon, okay? And just now I have told you, if your substituents are at internal carbon, that electron withdrawing group and that electron donating, they will be at 1 4 with respect to each other. And I have told you reason also. If oxygen lone pair will go there, sorry, negative charge will come here, and this negative is going to uh, uh, attach to your this carbon, because this will be positive, positive, negative. Okay. If you draw charges in rough, you will get to know which regioisomer will be major. So keeping that in mind, your OMe and CN should be 1,4 to each other. 1,4. Why? Because among OMe and CH3, this is more electron donating due to its plus M. Now in first option you can see that 1, 2, 3. 1, 3 relation is there. Okay. So option A will be eliminated. In this 1, 2, 3, 4, yes, this can be possible. 1, 2, 3, this is again wrong. So among B and D, Aarti, which option do you think is more appropriate? Option number D. Why?
Why?
Because
Because
first
One
of
four
all,
product.
first of
OME
all,
and CN are at
OME and
1,4
CNR.
relation. Okay. Another thing is your CN is facing endo side. Yes or no? So correct answer is option number D. Have you understood? Okay. Let's move ahead. Try to solve this question. This is another example of your Diels-Alder reaction and tell me among these four options which is most appropriate. In first case, heating is given. Second, butyl lithium followed by aldehyde. Just try to figure out how will you solve this question. And let me also solve since this substituent is at internal carbon, not at terminal carbon. Okay, it will give you 1,4 product. This thing is clear. 1,4 1 2 3 1,4 I am telling with respect to carbon attached to substituent. Okay, and this pph3 will be here. This pph3 is already positive. Okay, so your first intermediate will be this. Then butyl lithium is there. Butyl lithium is obviously is going to take this proton. Why? As this is near to your phosphorus which is positively charged. So here it will form ylide. Now they are reacting it with benzaldehyde. So you all know that which reaction. This is simple your Wittig reaction. Now question arises, either it is stabilized ylide or unstabilized ylide. I don't know the stereochemistry of pH. It can be both way around. This is also possible and this is also possible. These options are eliminated because they are 1 3. So among C and D, Aarti, which option do you think will be most appropriate? Okay, C. Let's see. Yes, very good. Option C will be correct. Why? Because this is not your stabilized elide. This is your unstabilized elide. And if you don't know what is your stabilized elide, let me tell you, there should be any group which can stabilize this negative charge. But these are alkyl groups only. So this is your unstabilized elide. And we know that stabilized elide give E and unstabilized elide give Z. So obviously this will be correct. This is Z. Priority 1, Z. Very good, Aarti. Next question for you is this. Tell me which reaction you think is possible here. Electrocyclic, Diels-Alder, and moreover, you have also studied in pericyclic sigma-tropic reaction. So these are hint for you. Now tell me which option can be correct. Take your time and then tell me. don't see its solution. I am solving here, and just write answer in your chat box. So here, one, two, three, one, two, three. So basically, it will be your which type of rearrangement? Cope or Claisen? This is your oxycope. Why? Because car oxygen is attached. But if one of the thing is your oxygen, where you have numbered, then it will be Claisen. Okay. So let's make the product directly like this. Here double bond will come. This bond has broken. Okay. Here OH will come. This OH will tautomerize and will give you this product. So option C is most appropriate. I hope you got it this Aarti. So correct option is option number C. Then try this question. This question is similar to previous one. Tell me among these options, which option is most appropriate or correct? Okay. Option B. Let's see. So in option B, I think you have done 2 plus 2. In order to get option B, only 2 plus 2. But you should know this thing that 2 plus 2 reaction between two olefins occurs in photochemical condition. But here heating is there. So 2 plus 2 can't be possible. Okay, Arti. So next possibility is your 1, 2, 3, 1, 2, 3. Sigma tropic. And when you will do sigma tropic, you will find out that option A, you will be able to form option number A. Let me draw for you. Wait. Okay. This double bond will come here. This bond has broken. This 5 membered ring will be as it is. Okay. And here double bond will come again, and this bond will form. Okay, now you can count. One, 2, 3, 4, 5, 6, 7, 8. So yes, 5, 8, 5. 5, 8, 5. Okay. Double bonds are there? Yes, double bonds are there. So most appropriate answer is A. This has been formed by 3, 3 sigma tropic. This has been formed by 2 plus 2, but it is not possible because heating condition is there. Okay. Now your homework is, Aarti, you find out that how they can write these options. Okay. Which rearrangement can lead to option number C and D. Okay. Let's move to next question. Major product formed in the given reaction and mode of rotation is. So Aarti, before solving this question, tell me which type of system it is, 4n or 4n plus 2? 4n. Okay. 4n under heating condition will undergo which type of rotation? Cone rotation or disk rotation? But I think there is photochemical condition. Yes. Now tell me, 4n system under photochemical condition will undergo cone rotation or disk rotation? Disk. Very good. So your job is done. You know that this is 4n system. This is photochemical condition. So obviously it will undergo disk rotation. So you can easily eliminate option number A and option number B. Only left options are option number, oh sorry, this is your D only. Now in C and D, tell me, Aarti, which option can be correct? C and D. See, if you draw this uh, die like this, so let's say CH3 is there, pH is there, pH is there, and CH3 is there. I can't draw like this pH. Now you see that CH3 and CH3 are trans to each other. pH and pH are also trans to each other. You know that foreign system under HMU condition undergo disk rotation. So the things which are, you listen again. So the things which are trans in your starting material, if they will undergo disk rotation, they will cis in product. Okay. So option number C is most correct because here CH3, both the CH3 are cis. Why? Because since this system is under, okay, for your understanding, let me tell you one special thing that I have noticed in this reaction. Dekho, see, these CH3 are opposite, okay, and these pH are also opposite. One is going down, another is going above. So they are opposite, right? On disk rotation, opposite things will go under cis. And if instead of disk rotation, cone rotation is there, opposite things will become what? They will be opposite in your product also. Means they will be trans in your product also. So this is the, you can say that this is trick. In cone rotation, whatever groups are whatever group stereo is in your starting material, it will retain in product. But if this rotation is taking place, your opposite groups will become cis and your same side group will become trans. I hope I am clear here. Okay, so this is your question number 6. uh, Basically this alpha beta unsaturated ketone is made to react with this alkyne containing two aliphatic aldehydes, CHO. First, heating condition is there. Second, is your hydrolysis, acidic hydrolysis. So tell me, what will be your first step by looking at this question? Ma'am, here also the, see, that line rule is only for Diels-Alder reaction, Aarti. Okay, only. For electrocyclic reaction, you have to see the groups in starting material, and on basis of rotation, you will tell whether they will be cis or trans. But that line rule which I have told you, please apply that rule only in Diels-Alder reaction. Okay. Now in this last question, tell me, which will be your, what will be your first step? Heating condition is there. 2 plus 2 reaction can't take place because heating condition is there. Another thing is, if you have attended my previous lecture, I have told you, whenever you see cyclobutene, cyclobutene. Okay, and heating or photochemical condition is there. First step will be your electrocyclic ring opening. Okay, so I have given you hint. First step is your electrocyclic ring opening. You also start solving. I am also solving. So this bond will go there and this bond will go there. And first intermediate you will get is OMe, OMe. Now things are clear. Okay, you have your dyne, you have your dieno5. You just have to do 4 plus 2. Okay. This is electrocyclic ring opening followed by your Diels-Alder reaction. That is your 4 plus 2 cycloaddition. What you will get? This will be your OMe. This will be your OMe. CHO. CHO. Understood? And at last acidic hydrolysis is there. So this acetal will change into ketone. I hope you know the mechanism. Basically, in acidic condition, one of the methoxy will be protonated, other will knock off this methanol, and then at last, after workup, you will get which option is correct. This can't be true because acidic hydrolysis is done. Among these two options, let me draw for you. This is your CHO, CHO, and double bond O. Okay. Either which option is more appropriate? Option number B or option number C? Can it undergo tautomerism? Option number B. Yes. Option number B here is more appropriate because tautomerism is your 1,3 hydrogen migration. Okay. So here option number B is correct. This is your last question. Then we will move to photochemistry. With respect to the following biogenetic conversion of corysmic acid A to 4-hydroxyphenyl pyruvic acid C, the correct statement is basically Arti. Here you have to draw mechanism how you have gone through A to C, and then tell under which rearrangement they have transformed this. Okay, I am also solving. So one thing is clear here, Clausian type of rearrangement is visible. One, two, three. Let me redraw here. One, two, three, and one, two, three. Basically, you have to join three to three, and this bond will break. Okay, and what you will get? This bond has shifted here. This COH will be as it is. It will connect to any carbon. This carbon. Okay. This is your COH and this is your double bond O. Understood? So you can see that you got this. OH is also there, okay. Only thing is left is oxidative decarboxylation. Okay, from here negative charge, as you know, on when COH leave as CO negative, it will leave here negative charge that will come back and will lead to formation of C. So correct answer is option number A. Understood? No dehydration has taken place here because here decarboxylation has taken place. Oh, one more question is there. Okay, try try to solve this question. Hint is your Clausian rearrangement. One of the product I am drawing for you, another product you can draw at your home. Okay. So one, two, three, one, two, three. So what you will get? So basically this bond will come here, this will go there, and this one bond will break. This is your cyclic concerted state, right? One mistake I have done is here double bond will be not there. So double bond O, this bond will go here, okay, students. This is your C14 labeled carbon. Basically, it is isotope of carbon. Just to have a glance at mechanism. I hope things are clear till this point. Okay. So, let me tell you answer here. Basically, first Clausian rearrangement will take place. Okay. 1, 2, 3, 1, 2, 3. Clausian rearrangement, I have formed products same in the same way as they have formed. Another possibility is that this Clausian rearrangement can take place from left side also. If you draw that double bond here, I hope you got it. If you draw another form of benzene in which double bond is there, that possibility is also there. So one possibility, second possibility. Now, one, two, three, one, two, three. Here, cope reaction. This is your Clausian followed by cope. That can lead to formation of these. I hope I am clear. Okay, let me write here. This reaction is your. This is very important question for your competitive exam also. This reaction is your Clausian followed by cope reaction. Understood? Okay. So this is next. It is 2 plus 2 cycloaddition. So it is clearly written over here that 2 plus 2 cycloaddition reaction can't take place in heating condition. Okay. By looking at these orbitals, you will get to know that under photochemical condition, that suprafacial interaction can take place. Okay. I will not go in deep. I have to revise all the things. This is your cheletropic reaction. In cheletropic reaction, on the same atom, you should remember, on the same atom sigma bond will leave and on same atom sigma bond will form. For example, let me give you a hint. Let's say you are given this. let's say you are given this with cyclopentadiene. I think I'm again for. I will give you another example for this. But right now you can see that on same atom these two carbons are getting attached. Okay. So two sigma bonds are formed on sulfur. This is your example of ene reaction. Intermolecular ene reaction. This is your intramolecular ene reaction. How inter? This is your hydrogen. This will go in this way, attack to your alpha beta carbonyl chloride, and will lead to formation of this system. Okay. I hope this is clear. This is basically 1 5 hydrogen shift. One, 2, 3, 4, 5. Okay. And this is your in reaction followed by only in reaction. And in intramolecular in reaction, they can be further divided into three types on the basis of connectivity only. Okay. Now we are done with our pericyclic chemistry. So basically in pericyclic reaction, main reactions are your electrocyclic, 4 pi, 4n system, 4n plus 2 system. Then comes your cycloaddition. Cycloaddition 2 plus 2 is there, and 4 plus 2. 4 plus 2 is more important as it considers D-Salter reaction. You should know regiochemistry, stereochemistry of D-Salter reaction. You should know why 2 plus 2 reaction between two olefins can't take place in heating condition. You have to draw those molecular orbitals and see their suprafacial interaction is possible under which condition. You know how to draw homolumo. From that you can draw. Okay. And then we move to sigmatropic rearrangement. Sigmatropic rearrangement, mainly there are two main reactions in that: three Claisen rearrangement and Cope rearrangement. In Claisen rearrangement, one of the atom is your oxygen, and in Cope, all the atoms are your carbon. Okay. So now let's move ahead to Norrish type 1, and basically in this slide I am going to cover all the photochemical reactions which sir have taught to you. So whenever your carbonyl compounds are left in photochemical condition, type 1 reaction is your Norrish type 1. Alpha cleavage take place from here. Okay, this is your alpha carbon, so alpha cleavage to carbon. When you will cleave, this radical will form. This radical is known as your acyl radical, and one is your alkyl radical. Then this CO can leave, leading to formation of R radical. These two radicals can combine, leading to formation of this alkane. Okay, this is your Norrish type 1. In Norrish type 2, both the possibilities are there that alpha cleavage can occur from both the side, and other possibility is you have alpha, beta, gamma hydrogen abstraction. When gamma hydrogen abstraction takes place, let me draw for you for understanding. Wait. This is your gamma hydrogen, right? When you cleave this carbonyl into radical form, this pi bond, okay, this O radical abstract this gamma hydrogen, leading to formation of alcohol. Now leaving here radical, okay, here also radical is there. Okay. Now two possibilities are there. One is this bond can cleave from here, leading to formation of these two products. Radical combine, leading to formation of alkene, and here carbon. Another possibility is also there that they can form this cyclobutanol. Okay. So these are the possibilities of your Norrish type 1 reaction and Norrish type 2. I hope it is clear. Next comes your dipymethane rearrangement. So students, in dipymethane rearrangement, let me draw. Again, this is your starting material, okay? So first you have to make biradical at one side. The sequence to do these type of questions. First you have to make biradical at one side. Then you cleave this also right side and make cyclopropane. Okay, so radicals are there. Now you have to keep one thing in mind. You first started from right side, okay? You have to cleave the cyclopropane from side opposite to side from where you have started. If you have started from right side, you have to cleave this bond. Okay. If you will cleave this bond, radical will combine will lead to formation of alkene. And this radical will combine here in order to get this cyclopropane. Okay, Aarti. So how I have started, let's say in this case, they have started making biradical from left side, okay? Then they have formed this cyclopropane. Actually, this intermediate is different, but for question solving purpose, you should remember this thing. If you are starting from this side, let's say, okay, then you have to make this cyclopropane. You just open that cyclopropane from side opposite to you have started. If you have started from here, you have to break this bond. If you have started from this side, you have to break that bond, because this type of thing will help when diene will be unsymmetrical. How? Let me tell you. Let's say here Me is there and here phenyl groups are there. So obviously first you will make radical this side, because here radical will be stabilized by these two phenyl groups. Okay, so at first you will make this radical. Now cyclopropane will form. Understood? After that, I have told you have started from there, so you have to break this. And the reason or logic behind is that I will tell you. See, if you are breaking this bond, okay, it will leave here radical in both the way. Here also, if you break this bond also, radical will come here. If you break this bond also, radical will come here. But in these two radicals, this radical is relatively more stable, yes or no? So it can remain in radical form to longer time. Okay, so therefore we are cleaving this bond so that you can quench this radical as soon as possible, because this is not stable. Therefore, this olefin is forming here, and another radical will combine with this in order to form this cyclopropane. I hope you have understood. Yes or no? Dipymethane rearrangement. If you have any doubt, you can ask me. Understood, na Aarti? Okay. So let me erase all this. So next comes Barton reaction. In Barton reaction, your alcohol is converted to nitrite. Now you have alpha, beta, gamma, delta. So in Barton reaction, you should remember in Norris type 2 reaction, gamma hydrogen abstraction is there. Gamma hydrogen abstraction. Okay. But in Barton, delta hydrogen abstraction is there. So in HMU condition, here it will form radical. This bond is most prone to cleave. So alkoxy radical will form and alpha, beta, gamma, delta. Delta position hydrogen will be abstracted by this alkoxy radical, leaving here radical. Okay. Then this radical will be combining with your NO, forming this oxime. On tautomers, it will get. Sorry, First, on combining with NO radical, it will form this. On tautomers, it will go to oxime, which on hydrolysis will lead to formation of aldehyde at this oxime. Okay. So basically, whenever you get questions of Barton reaction, you have to draw aldehyde at delta carbon. Okay. Next reaction comes is your De-Mayo reaction. In De-Mayo reaction, students, your 1,3-diketone is your starting material. Okay. This 1,3-diketone can undergo tautomeres, right? On tautomeres, it will change to its enol form. Then an olefin is given to you. That ketoenol form will undergo 2 plus 2 cycloaddition with your olefin, leading to formation of beta hydroxyketone. And you should know that beta hydroxyketone are product of aldol. So it can undergo retroaldol in this condition. This OH bond will go there, go here, and it will cleave this bond. Okay, leading to formation of 1,5-diketone. So if you see the transformation, you have converted 1,3-diketone to 1,5-diketone. Okay. Only thing you have done is you have sandwiched this olefin. You have sandwiched this olefin between these two diketone partners. Yes or no? See, this one was your diketone. You just have sandwiched this olefin between your diketone partners. Therefore, they have become 1,5-diketone. So this is very beautiful reaction for application purpose, right? You can directly change 1,3-diketone to 1,5 by inserting a olefin between them. Okay. Last is your Paterno-Bucchi reaction. So this reaction is nothing but your 2 plus 2 cycloaddition reaction between your olefin and ketone, which under photochemical condition lead to formation of this four-membered ring or oxidase. Okay. Regiochemistry you can see in same way as we have learned for dipymethane rearrangement. Combine those radicals first which are less stable, and at last combine those radicals which are more stable. Okay. And we have come to end of the this course thing. At the end of the course, sir have told you how basically he have told you photochemistry of aromatic compound. So let's start from here. This is your benzene S not ground state. Okay. If you have H mu and you are giving light of wavelength less than 254 nanometer, which means it is near vacuum region. Here it will undergo in biradical way. Biradical way will lead to formation of your Divar benzene. Okay. In presence of 254 nanometer, it will undergo singlet excited state. That okay. Let me start. Let me tell you from basic. Okay. Let's say you have your benzene. Okay. You can write it's one of the resonating form like this, positive, negative, and like this. Okay. Now for this, you can see this negative charge is at basically this positive charge is outside. So let's draw one more resonating structure. Negative, this positive will be here, and this will be there. Understood till this point? Now now you have to quench this basically. This Okay, if we have to draw its resonating form in normal form, what we will do, we will quench this. But in this photochemical reaction, what you have to do, you have to form cyclopropane. Okay, in order to form cyclopropane, this carbon should carry positive charge that can combine with this negative charge. Okay, so here positive charge is already there, positive negative, but this positive has also left here negative charge. So in this way they have formed this. And why they have written like this? Because this is allylic. This positive charge can go there, this positive charge can be here. So in this way, in singlet excite, this is your triplet excited state. That's why it has went through biradical form and led to formation of radical, 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 radical. Okay, these radical will combine and this radical will form benzene. And in S1 excited state, so let me write here, it has gone from S node to T1. So if anyone asks you in exam, biradical form, benzene will form under which condition? It will form when it will undergo S node to triplet excited state. But when it go or S node to S1 singlet excited state, it will go through your zwitterionic form. Okay. Now from this zwitterionic form, you can get these two. How? If you this is your zwitterionic form, right? You can directly combine these positive, negative, and you will get this. And in same way, on a rearrangement, you will get fulvalene. This is your full, sorry, not full. This is your fullerene. This is your benzoylene. Okay. And this reaction is simple. CH3 in deuterated methanol. This is your OCH3 negative, uh, which will be quenched by this positive charge, and this negative charge will be abstracted by your deuterium. And this is the summary for photochemistry of benzene. Now let's move to photochemistry of singlet oxygen. Now why singlet oxygen? Because in in atmosphere that in atmosphere which molecular oxygen is there, that is found in triplet form. Because if you know something about molecular orbital of oxygen, you can see that in last two orbitals they are in this form. Sorry, if you draw molecular orbitals of oxygen in last two orbitals, they are like this. So they are in triplet form. This means triplet form of oxygen is stable. So in which form it is going to react? Obviously in singlet form. So whenever in on arrow it is giving O2, any photosensitizer will be given to you and photochemical condition will be there. Because photosensitizer will convert your oxygen, triplet oxygen to your singlet oxygen. Now this singlet oxygen can undergo various reactions. This can undergo 2 plus 2 cycloaddition to give you dioxetane type intermediate. This can also undergo your 4 plus 2 cycloaddition, which can give you this peroxide, right? And moreover, this oxygen can also undergo ene reaction that will give you allylic hydroperoxide. Understood? Basically, this bond will shift here and will leading to formation of allylic hydroperoxide. So this is the short summary which we have learned in last 8 to 9 weeks, starting from electrocyclic, photochemistry of singlet oxygen. I hope I am clear. If there are any doubts, please ask me. Thank you. Let me go from starting. Aarti, are you having any doubt in any of the slide? I can explain you again. Or any of the topic which you have not understood in lecture. Photo-induced reaction. Can you tell me the problems based on this topic? Photo-induced reaction means reactions which are driven by your photo. Okay, that donor acceptor concept. Basically, Aarti, in that donor, actually, I don't have problems related to that concept here. But one thing that I can tell you from this, wait, let me see an example. Let's say you have this compound, right? And let's say you have this here. So from here, you can easily see this molecule is electron rich, right? So, in that photo-induced reaction, there are two things. One is your donor, one is your acceptor. Okay. So, among these, you have to see electronic nature. This looks like more electron-rich system, so it will behave as donor. This is your acceptor. Okay. So, donor. Let's say you are having donor atom. In photochemical condition, it will be having radical and it will donate. Since it is donor, it will donate. Since it is donor, it will donate, and on donation, it will become radical cation. So, your donor will become radical cation. You can understand from this. Let's say your donor is oxygen atom. It is having lone pair, right? Let's say it has given one of the electron to any acceptor which can accept. So let's say acceptor is there. You can directly get product. Another thing is that your acceptor on accepting what it will form radical anion. So one possibility is that the donor acceptor combines and give you product. Another is your, I don't remember that term, back reaction. What in that reaction your donor acceptor will combine and again leading to formation of starting material. Okay, let's say you have acceptor. Acceptor will first accept an electron and will lead to formation of radical anion, right? And whenever you will give its donor. Obviously, acceptor work is to accept. So it will form its radical cation because it will abstract that radical from donor only and can lead to formation of product. So this is a basic concept. You will not get much question based on this concept, but you should know that whatever electron rich part is this, that will be your donor, and electron deficient will be your acceptor. Actually, I have not kept problems based on that. Okay, but I hope it is clear. You just have to see electronic nature of that compound. Okay. Okay. So that's all. Thank you for joining the class. Thank you.